Avery, welcome to Validate It.
It's great to be here, Austin.
Yeah, excited to have you on. You have recently stepped into a new role on the Aptos project, but you've been involved since the beginning. What's your new role? Let's kind of start out there.
Sure. I'm CEO of Aptos Labs. And to your question earlier, I've been involved in this project since pretty much the early days at Meta when it was known as Libra and Diem.
Yeah. So I actually worked on some of the Libra Diem stuff back in the day at Bison Trails. We were part of the technical steering committee, and we're looking at building up a bunch of infra to support it. Then we unfortunately finally got the launch of Libra just a few weeks ago from the president of Argentina, but not the one we were hoping for.
Not the one we were looking for, yes.
No. So I'm kind of curious, how did you get into the space initially? Was Libra the first crypto thing you kind of came across when you were back at Facebook, now Meta? Or had you kind of been interested in the space for a while before that?
I had read the Bitcoin white paper, I think a while back, probably in 2016. And I just, for someone who's been involved in distributed systems kind of my whole career, starting from my PhD, it was fascinating to see how you could secure a network with economic principles. Definitely, I think there's a lot of work that can be done in the how to optimize the protocols, but I think just the soundness of the idea of how economics can secure a protocol is just an amazing concept. And then the direct ability for consumers to interact with that protocol is incredible as well. And so that's kind of my early interest. What I was working on at Meta at that time, though, was data infrastructure. I was working on the systems like Spark and Hadoop and Hive and others. Graph processing to process kind of exabytes of data that come from Facebook servers and then turn that data into actionable insights for products. And then there was this new effort started at Meta where we weren't sure exactly what we were going to do, but figured out over time that supporting payments for everyone kind of in the world, not just Meta customers, but number in the billions, but seeing Uber, Lyft, and others, and you're very familiar with this since you were on the Bison Trail side, was a very meaningful goal, I think, for society and something I got very passionate about.
Yeah, it was one of those visions where it seems like it just hit the wrong moment in society where everyone was mad at Facebook for a bunch of other things. And so this sort of just felt like, oh, we're going to give them the money too. But, the core concept is pretty ahead of its time, right? That we need a whole bunch of different international stablecoins. And I think, Dan Smith, maybe from Blockworks, tweeted out a chart a few days ago, which was stablecoin issuance on chain relative to price, and price is bouncing all over the place, but stablecoin issuance is solidly up even through all the market turmoil. So I'm kind of curious, when you guys were then thinking, okay, maybe we should take some of the stuff we worked on and go build some type of blockchain system outside of the Meta world. Why did you not think we're going to build Stellar 2.0? Why was a payment network not the thing you decided to go build?
I think the thought initially was this technology is still very nascent and it's hard to see, what it's going to be useful for in the future. And with that in mind, that was the way that Diem was actually designed as a blockchain. And one of the key core concepts was upgradability.
Yeah.
Because we knew the protocols were going to change a lot. The consensus protocol would change, our design would change. We would learn new things. It's just a very early time in green fields for all of crypto, I'd say. And even now, there's still many new ideas being proposed. And there's definitely some consensus on certain ideas, but things like dynamic parallelism or block STM is gaining a lot of traction. Move is gaining more traction. But there's still a lot left to do here. Many
Sure.
more 10x ideas. Our thought was this technology has the potential to impact 5 billion internet users, and what they want to do, the payments is definitely a piece of that, but it's not the only piece. And I think blockchains are really good at moving assets from one person to another, or from one business to another, in a way that no other system can replicate. And the goal is really how do we make that occur as smoothly and as quickly and as efficiently as possible.
Yeah, so I kind of want to get into there's a lot of far future stuff about blockchain that is kind of applicable to any network, and really anyone building a fast blockchain nowadays can talk about a world with permissionless money, a world where, all types of information and asset are tradable on chain, but we're still unfortunately a ways out from that version of the future. So I want to kind of dig into a bunch of we'll get into the whole technical side of Aptos in a minute, but from a philosophical standpoint, what is Aptos trying to accomplish? And how has that informed some of the design decisions of the protocol?
Right. So I think there's kind of two things Aptos is trying to accomplish. From a technology perspective, I think it's all about money movement, as we just talked about. And so being able to support very, very efficient trading primitives on chain, being able to support stablecoin movement for cross-border and remittance, as well as other use cases. And then the last thing is seeing RWAs really proliferate are kind of the key focus areas for how we think about money movement and the key technology advances you'll see and how they apply to those. The other thing, though, and I think this is something that I have to give a lot of credit to Solana for doing, is like, how do you build really large billionaire unicorn type businesses on top of the protocol and seeing that ecosystem grow, right? And I think that those two focuses, like if I had to kind of put it very succinctly, are the key of what Aptos is trying to accomplish. We have, a country with incredible infrastructure. We call Aptos. People can zoom around the roads extremely fast. There's great decentralized governance, on-chain governance. There's incredibly low fees. You can get, an example I might say is like Michelin star meals at a fraction of a penny. So all the infrastructure is there. Now we've got to get the businesses to build their incredible products and see their visions kind of reach full fruition in the country.
So like if I roll back to like 2020, like late 2020 is when I got involved in the Solana ecosystem. Back then it was hard to get people to build on Solana, but once you sold them on the concept of building on a fast blockchain, it was the only one out there. Like there was no fast blockchain at the time besides Solana. We fast forward now and we're in a pretty different space, right? There are L2s that are like fairly fast, we'll see, but like we have Mega ETH, which will be like much faster coming. There's a lot of fast L1s out there now, from Solana to, Sui to Aptos to, other types of networks as well. Like when you're thinking about the pitch of like why of all the fast places you can build, Aptos should be that one, like, there's no one blockchain that's the right choice for every founder, but what are the characteristics of projects or founders that you think are well suited to the technology that Aptos has?
Yeah, it's a good question. I think what it comes down to is just what are the real kind of differentiators that Aptos has compared to other networks.
Yeah.
And so I think there's three that we focus on from a kind of a more systems perspective. And then there's a UI, UX kind of perspective that also I think there's some significant differentiators here. So from the systems perspective, for infrastructure, you want to be kind of three things: more scalable, more cheap, and more fast.
Yeah.
There's a lot of FUD in the space, and there's a lot of different kind of claims. And I think for us, what we really try to do is make sure that whenever we make a claim about performance, speed, or cost, it's got data behind it. And we really look at the reproducibility of those benchmarks. So I can give a couple of examples for all three of them. So for scalability, what we saw is in August of last year, just a couple months ago, really, Aptos was able to show you could do 326 million transactions through an ecosystem game that were actually quite complex, hitting the same shared state and doing more than 37 transactions per second without any downtime, without any impact on fees, without any impact on other applications. That's a key concept, I think, that you need to have for an infrastructure to be trusted. And I kind of go back to this thought of like cloud computing was in the early days not trusted because it was not reliable. It was expensive, and it was security concerns and all kinds of things like that. Aptos has demonstrated that you can actually start to run really large scale applications at scale, reliably, and at very low fees in a production mainnet. That's a really, I think, a good example. Another example that might be though showing experiments that happen in kind of what we call preview net, and I would love to see other networks do the same, where you can kind of spin up your network yourself, see exactly the experimental configurations that are run. And for that, we showed that for like about 120 validators, which is not dissimilar in size to our existing mainnet with also country geographical distribution, we could do more than 2 billion transactions in a day, which is more than Visa, MasterCard, and every other payments network kind of put together and combined. So that also shows like, the world that it's ready for large scale payment infrastructure.
Sure.
And also, like, if you don't believe us, rerun the experiment and you'll come with the exact same number. It's a bit of an expensive experiment. We tell you exactly how to do it. It's on GCP. Here's a hardware configuration. Here's a software to use for it. Here's a version of the software to use. And here's the testing script we used. And people can all run that experiment themselves. And I would love to see more of this happen in our industry. Unfortunately, it's not as common as we would like. It's common in other industries, though, like in the database industry, you have things like TPC benchmarks that are well run with experimental configurations. In the supercomputing world, which is where I come from, Top 500 has the kind of LinPack benchmark that's run repeatedly. So our industry will get there. For us, we like to think that we're hoping to set the standard and leading the charge here. And the more you start to see the differentiation, while people might claim, we're all like high performance blockchains, I think there are really different performance characteristics you'll see when it comes to the scale. For latency, the same thing. We have an open source latency dashboard we publish, and all the codes there are open source as well. We run the experiments on kind of a lot of different networks, showing that Aptos has got the lowest user-based latency, which is what I think people care about the most. Sub-second, usually around 700, 800 milliseconds. And at load, what happens is a good question you'll probably want to discuss.
Sure.
At load, that's where we can kind of observe real time as the transaction workload goes up, what happens to load, and that's something that's, I think, helping to show, like, there are differentiations in these products. Aptos is the fastest, and you can see on our dashboards. And then from a cost perspective, that one's probably the easiest one. There's two types of costs I think we think about. One is more like the cost when there's no like demand-based pricing. So whenever you're under capacity of the blockchain.
Sure. Base fees.
Yeah. That's where Aptos, like for Tether, is like 1/100 of a cent to move money around. That's by far the cheapest. And then when it comes back to our point about scalability, since we can push the scalability limit so far, the demand-based pricing does not kick in. And then we've never seen it kick in because no one's actually pushed the limit of what Aptos mainnet can do.
Sure.
But all blockchains kind of perform the same, and when you hit a demand-based pricing, because at that point it's not about the cost of the network. It's more about the cost in comparison to other transactions.
So it's funny, you're talking a lot about like benchmarks, because one of the things I think before we need benchmarks is like common definitions on what words mean, because it feels like every L1 has their own version of Church Latin describing exactly, on Ethereum, a validator is actually only 32 bundle of ETH wrapped in a smart contract, whereas like on Solana, it's a server with like 256 gigs of RAM sitting in a data center somewhere. And they're just like very different definitions. So I kind of want to start off, before we get into more of like the how and the what, of like, give me the architectural overview of Aptos today. How do transactions move through the network? How does data flow work? What is the consensus model? Like, let's get into a little bit of the high level systems architecture.
Perfect. So one of the things we did, besides, I think, having this upgradability that was really good for us, was the idea of a modular design from an infrastructure perspective. And so we split up the phases of transaction execution into 5 distinct phases. There's a data dissemination phase, there is an ordering phase, a parallel execution phase, a commit phase, as well as a storage phase. And by doing this, that allows you to kind of modify any of these components individually without having to affect the others, and not having to worry about the code spaghetti that happens when you have a big, giant, totally monolithic design. This is not the same, though, as the kind of modular design people think about today in terms of kind of composing different pieces of blockchain together. It's more about how do you kind of build reusable and reliable components as a general purpose software engineering concept.
I'm also not sure that Twitter version of modular blockchain even exists.
That's fair. And so for us, we have these 5 phases of kind of transaction execution. And the great thing about this is when you think about, what allows a blockchain to be extremely high performance, is being able to leverage all the resources available to that validator. And by having each of these phases kind of operate individually and in parallel themselves, and leverage those resources, you can then take advantage of all the CPU, all the memory, all the network capacity, the storage capacity, so IOPS. And then also over time, what we've been able to show with some of our new research, you can actually expand these validators to be multi-machine hardware clusters and take advantage of a very fast network, and then support even larger amounts of throughput at low cost.
So when you say you have phases, what does that actually mean? Because I think what people are familiar with, you've got pipelining, like Monad does EVM pipelining, right? So it's you have multiple things sort of moving through pipelines at different stages, and they would call that different phases.
Yeah.
What do different phases mean for you guys?
So for us, I think a lot of people talk about asynchronous execution in both Monad and Solana. And so that's kind of 2 phases in some sense. You have this consensus and you have execution piece. But for us, we think of many other parts of the transaction execution happening in parallel. For instance, the data dissemination layer that happens very distinctly in Aptos is always on. It's always taking transactions, bundling them together. So the way it kind of works, and I'll just describe it very simply, is every validator can receive transactions. Every validator then produces a kind of group of transactions that's then sent to other validators, and then kind of get this kind of what we call proof of availability, and then broadcast that to other nodes. And this happens continuously. For the ordering phase, you're taking these proof availabilities and kind of bundling them together into ordering of them. And so at that point, you're not having to send around the data again, which is fantastic, right? And these processes are happening at the same time. There's no like waiting for one or waiting for the other. They're all consistently going over and over. And then you can think about the parallel execution phase as it's a bunch of CPUs just kind of sitting there, seeing now these kind of ordered blocks of transactions coming in and deciding how to process them. And then that's really
sorry,
nice.
I just want to I want to break down some of these components, right? So you have so Solana, there's no mempool. Ethereum has a mempool. Maybe a fair analogy is it sounds like there's sort of this general availability, which one could almost describe as a function similar to a mempool, where there's this constantly throwing ether, not to use a charged term, of transactions, and then something is building bundles out from that. So are these basically a leader rotation schedule where different validators are given time slots to build blocks in or build bundles in, or how are those bundles and that ordering decided upon?
This is a good question you're bringing up, because it's pretty key to how we achieve massive throughput. The goal is that every validator is actually building bundles at the same time.
Right.
And as long as these bundles then are they have this proof of availability attached to them, they can be all kind of ordered at once. And so you're ordering the proof of availabilities, but not bundling one at a time.
Okay, but wouldn't those bundles be built differently depending on the whims of a particular block builder at that time?
They are. So that's why, so each of these kind of validators are generating these bundles. They're doing it quickly as possible. They're not executing them. They're just they're doing some simple validation. And you can imagine a world where, they can actually they can actually do a lot of transaction validation, signature validation, all that stuff ahead of time to keep it out of the system, but they're not required to. And since everyone is actually generating these kind of groupings together, we call them batches of transactions, and then the provabilities, there is a very nice scalability property here that makes it simple for validators to actually scale this out and kind of even increase their bandwidth, right? So again, if you imagine a world where validators get bigger and fatter, they and more machines and more network, not to talk about 000, there's a world where they can actually then process lots and lots of transactions, not just by themselves, but others are doing the same. Like every validator is kind of generating these bundles at once, and then these kind of proof of abilities are then being ordered through consensus. So the consensus protocol is not bottlenecked by the amount of data at all. These are just summaries of the data that's moving around.
Yeah. So I guess the part that I'm trying to get the mental model in is, so we have a bunch of amino acids, we form some proteins. How do we get to DNA? How do we get from a bunch of different assemblages of bundles of transactions that may not be the same or even replicated from one validator to another? How do we coalesce that into a block that then I look at in the Explorer?
Yeah. So what happens is those batches of transactions are being generated. Validators are consistently kind of distributing those throughout the network to make sure everybody has them. But there's a summary of those that have been signed off by a set of validators. Those summaries, of course, are much smaller in nature than the bundles of transactions, because it's just basically a hash instead of the actual data itself. So you can imagine, for instance, if you have half a K per transaction times 1,000 transactions, you're talking about 512K, half a megabyte, but could be summarized down to a small number of bytes.
Sure.
And so these kind of summaries are now being agreed upon in the ordering phase using the most optimal consensus algorithm possible, which is a three network hop consensus. And then once you have that agreement on those kind of summaries, you can then take those agreements, and then the parallel execution framework is seeing those agreements coming in and then says okay, here's the bundles that correlate to those agreements. And then I can go ahead and start to execute those bundles. And so this is all happening at the same time. So consensus is consistently producing things to add to the queue of parallel execution. Parallel execution is kind of consistently now looking at those kind of orderings and saying well, what do I want to do with that data? And that's where a lot of the magic comes in. So block STM is the way we process that, but it's just got the steady stream of transactions coming in order. And now you can deterministically figure out how do I want to process those transactions? And that can become very, very exciting and very interesting going forward.
Sure. I guess like there's a lot of different reasons that a block builder might choose to prioritize transactions in different ways, right? They could be
Sure.
maximizing for sandwich attack vector, or they could
They
be
could.
saying like, hey, I actually care about the things that are the highest fees, or I want to take the things that are lowest compute units. I'm sure you have some metric for how much compute a transaction takes first.
Right.
And especially as you get like more mature as an ecosystem, people are going to start building like very custom implementations of all of these types of tools and tricks. So like, how does it work today, and kind of how does that ordering get agreed upon in the future when you have like many independent tweaks and forks of your validator client, or your for MEV optimization and those sorts of things?
I completely agree, by the way, everything you just said. Like there's definitely a lot of art that goes into how those batches are being generated. Today that it's kind of simple. It's just based on the gas fees, and prioritizing based on the gas fees. But over time, I definitely expect these shapes and forms to evolve. What's interesting though is that while any validator kind of prioritize transactions however it wants to, the actual implementation of how the priority happens is actually only at the runtime phase, that third phase of execution, the parallel execution phase. And that's really cool because now the system can actually optimize for whatever objectives it deems important. So whether it's going to be, I can give you an example. There are competing goals between system throughput potentially and gas fees.
Yeah.
Like you might want to say like, well, I really, really want this transaction to execute first, but I've got a lot of other transactions that can execute as well. I could use my cores and use my storage. So what do I want to do, right? And I think that's where the system has a lot of flexibility in what it prioritizes. And so today, the way it works is that if there's no contention on these transactions, these kind of transactions move forward in the queue really quickly. Now, if there's contention, like local hotspots, you can still process. We have something called the execution pool. So it looks at a window of transactions, and then it kind of advances that forward. So as much as it can do without having to deal with the contentions, it will keep processing. And this is, again, how we get very, very high throughput when there's no contention. Obviously, it's contention.
Right.
Then there's going to be a problem where you don't want to be blocked. You don't want to block the non-contented transactions, and we don't do that in Aptos, which is fantastic. But if there is contention, that's where you want the priority fees to really drive the ordering of those transactions. And so it's a really nice kind of balance between the two. And then like I think the design of kind of waiting until runtime to decide that is a really nice optimization that I think Aptos is innovated on.
Yeah, it's interesting because like you go back to like totally talking about Solana in like 2019 and stuff, and the reason there was no fee market and no priority fee concept in the beginning is there was assumed there was going to be no contention. That it was all going to be bids and cancels, and it's just going to operate basically like the entire point of of Solana was one giant central limit order book, right, in the original day.
That's right.
And then you realize like, oh, the minute you have anything more complex than an order book, you will inevitably have contention, and that contention is in the most valuable parts of the stack, right?
100%.
It's that the markets that have the most have the least throughput and the most economic value is almost always the same market. It's a liquidation, right? It's an
100%.
NFT mint. It's those
100%.
sorts of things.
Yeah.
So I'm curious kind of how you like every network has their own kind of approach to this, right? On Solana, there's parallelization because transactions have to specify the state that they're going to use beforehand. So you can say, okay, there's 5,000 transactions that are trying to write to the same piece of state. We're going to throw them onto this core and they're going to fight over fees. And the other stuff we can like keep going without touching it. You have Monad, which is doing like deep pipelining, which like has some very interesting properties because like that's also what eventually killed the Pentium 4 architecture, was like getting too far ahead in like pipelining. But I'm kind of curious what you would answer as sort of like, what is the like at scale thesis of how high demand, high value, high willingness to pay prioritization like coexists in this bundle model with the low value transactions like a USDT transfer and doesn't end up boxing them out.
Yeah, so the way I think this comes down to how you implement the parallelization technique, to your point.
Yeah.
And so Solana and I think Sui to some degree have also like really attached to this static parallelism where you declare all your dependencies up front. And then based on that, the scheduler assumes those dependencies are true, and then will serialize all those operations upon contended state. Now, the concern we have with that is twofold. One is that by doing that, it kind of is very hard from a programming perspective sometimes to even predict up front what resources they want to touch. And so you either have to lock a large amount of state, or you have to kind of split up your logic into multiple steps, right? So if I'm trying to say like, well, I want to, in this transaction, I want to update a bid order on an order book. I don't know exactly like which part of the node, like the way it's simplest represented is as a tree structure. And I don't know which part of the tree I'm going to update because I don't know what the tree looks like until it's a data-dependent decision. So I've got to lock the entire tree. And now I've serialized all access to this order book. The cool thing about what Aptos does is it says, look, we support dynamic parallelism, which is something that from the very, very first day. And we're going to try to run these transactions in parallel. If they don't touch the same nodes in the tree, it actually will just go in parallel, which is really neat. And if they do, there'll be contention and they'll be kind of queued up. But it's a runtime decision and not a predetermined decision. And so that's really nice for us to be able to support. The other thing I will say, so it's nice from a you avoid this what we call the false sharing concept. It's kind of more of a general supercomputing concept of like you want to avoid the notion that you're actually contending when you're not really contending. Right. And then the other thing is that it allows you as a programmer a much simpler way to think about like most programmers don't think about like when they write code, like do I need to pass in all the data I'm accessing up front because that's kind of a pain in the neck. Sure. So I think those are two things we really love. Monad has actually gone down the same route as us to kind of like copy love the ideas from Block STM. And they're not the only ones, right? So has Polygon, Starkware, others in this space. And I think there's it just shows like they see the value in the dynamic parallelism that we kind of put forward. The other thing I'll say is that the dynamic parallelism doesn't mean you don't take the hints. So if programmers want to specify hints around what might be read and might be written, you can use those for scheduling. And it's just an additional piece of information you can use if you'd like to use that. But it's just more about, are you using all the information available to kind of optimize the concurrency you can get in the program? And that's where I think the Block STM is really, really unique and shines.
Yeah, it's interesting because like sitting down with a lot of like EVM devs, there's like one of the classic questions I've always had is like, why don't you just move an application from an L1 to an L2 and it gets peak demand? Right? Mm-hmm. Like, if we're like saturating the Uniswap on Ethereum L1, why don't you just move it up to an L2 temporarily? Like take a giant lock on that piece of state and move it up. And like, we can't take locks on state. Like, is the answer in EVM because you can't actually take a state lock on in EVM that's like actually usable in that type of way. So how does Block STM handle those type of components? Because you still have the EVM like spidering transaction where like you don't really know where it's going to end. So how can you maintain that it's not going to hit contention at some point?
So I think the thing is it might, right? And then that's where you kind of build these queues of contention. And so you have the queues of contention that are built up. But again, things that are not contended are happening kind of freely, continually. And so you're still leveraging all the resources out there. It's just,
but like Sui ran into this problem, right? Like the first version of Sui that launched, like FastPay was like super fast. And then like if you're trying to run DeFi, it was like 5 transactions per second. Because like anything that ran into contention, like just it got and there are implementation things, but like don't you always run into some sort of like with enough monkeys on enough typewriters, you get Shakespeare. Like with enough throughput in Block STM, you're gonna get like pipeline crashes because of contention.
No, that's really neat because what it does is it discerns the contention. Like, I guess there are 2 ways to kind of figure out contention, right? One is to specify it up front. Right. The other way is also to kind of learn it when you execute the transaction. So you learn all the things it's touching, right? And so Block STM can support both, obviously. Yeah. And then kind of just say like, so what, and see what happens, because oftentimes you don't know what you're touching, and so the only way to deal with that is either to add a lot of locks, which is painful and very expensive. And there's limits to that, or you need to lock like everything, or like I said, is execute indeterminate. And so I think the key thing here is that Block STM determines at runtime what it wants to do and how it wants to execute. It doesn't, it's not fixed on the idea of a static lock. And then for FastPay in particular, FastPay does not work well for DeFi at all. It doesn't, if you look at the metrics, by the way, FastPay is only used for transfers. Yeah. All DeFi is just contended state, like shared state. And that's where all those transactions happen. And that's where I think Aptos really, really shines, because we have very, very efficient methods of concurrency through Block STM, dynamic parallelism. And also there's other cool concepts like aggregators, which allow you to do, like, even though the state is shared, we can do those mostly in parallel. 99% of the operation happens in parallel. And that just allows you, again, our goal is to make the most highly concurrent shared state out there. And everything that Aptos has done, aggregators, block STM, and then like even the new things we're doing around what we call execution pool is all geared towards maximizing the throughput. And so it looks like we're all sharing the same state, and we are, but there's a lot of tricks behind the scenes on the system side to make each piece of that state execute almost as if it's like its own state and completely individualized and parallelizable. So that's the trick that we have to kind of getting massive throughput above other L1s.
Yeah, I think the place this really like is most apparent is in like the Shardines blog post that you guys put out maybe a few weeks ago, maybe a month ago. I forget exactly when.
Yeah.
First off, hilarious name. But like the second part that I kind of want to get into is like there were a lot of thoughts. Like I was around in like not like that early in crypto, but like late 2017, I kind of like joined the space, and this is when like the ETH2 conversations were still a little bit of a ways off, but you could start to sort of see them coalescing around this idea of like, we're going to have a beacon chain, we're going to have all these different shards attached to it, we're going to have these 20-minute checkpoints where things basically clear through a common like, host network, for lack of a better term, and then like we have updated state. And there were all these kind of questions around like, okay, but like, we're going to get a DeFi chain and then an NFT chain, and like, you can sort of squint and look at the current L2 world as like, maybe the worst version of what that sharding vision like could have been, because it like breaks the state and there's no common frameworks for how things communicate. And there's like 4 versions of the super chain, right? And like everyone's a super chain. But I'm kind of curious because like you guys have done, I think probably the non consensus
that's the way I was
at the
pick,
moment,
yes.
which is like to bring sharding back as a concept. And I'm kind of curious, like, how is this similar and how is this different from like trad sharding, if we can use that term?
Yeah. This is definitely the contrarian take. And the contrarian take that we have is that we want to see shared state scale as much as possible. And Shardines is just yet another implementation of that. And we want to push the boundaries because, as you kind of mentioned, the L2 world introduces a lot of friction for the users, having to kind of move from chain to chain to chain, or dealing with bridges, which are, of course, huge attack points. And I think for the user experience to be maximized, it's got to be a very, alongside having fast, scalable, cheap, it's got to be easy.
Yeah.
And so for this, our goal is like, how do we scale up the validators to actually do more work, even if it's not on a single machine? Because those limits are going to be hit, and so how do you kind of break beyond that? That's the work of Shardines, and we're leveraging very interesting algorithms around graph partitioning and other techniques to say like, well, let's farm out the work to a bunch of different CPUs. We load up the storage at the same time. We pipeline everything internally within those shards, and then what it shows is you can actually get very, very high throughput, and so you don't have to break your shared state in order to get 1 million TPS. You don't have to break,
like. Sorry, I just want to like. Sharding is inherently breaking the state, though. So like you're breaking it somewhere, right? Like maybe the effect on the VM is not fractured state, but it's somewhere you're making decisions about where to break stuff up, right?
Yeah. So the breaking happens internally on a validator.
Okay.
And so this allows also validators to have different infrastructure setups. It also does support that, right? So some validators could imagine have like, I don't know, 5 very powerful machines attached to it. Some might have 20 much weaker machines attached to it. And that kind of gives validators a little bit of flexibility and freedom in how they think about distributing the workload across their cluster of machines.
Yep.
But the main thing is that from a user perspective, everything looks identical to you. You still look like you have one shared state. And so this kind of goes back to my point earlier, which is like our job is to make everything look equivalent to you, as like we're all operating, in the same. We're on the same roads. It's still one highway, but in reality, what's happening is that we've we've made the highway extremely wide. It's got thousands of lanes. It's the highway's kind of magically like changing underneath your feet a little bit. You're going up and down different places. And this superhighway is allowing you to get throughput that nobody thought was possible. 1 million plus transactions end to end, and a single validator is an incredible achievement. And we think we can push this further. This should be able to push with like better hardware to 10 million plus. And that starts to get really, really exciting from what can blockchains do today into what blockchains can do tomorrow.
Yeah.
Bill Gates has a very famous quote of like, what would you do with more than 640K of RAM? Obviously, we know the answer is a lot after we see what AI
Chrome tabs.
and Chrome tabs and everything has done for us. Chrome, two very important innovations, Chrome tabs and OpenAI. But that I think will really unlock the door for massive innovation in the blockchain space as we see those throughput numbers, get really high.
Yeah. So like, it's a super interesting idea of like basically like you can take like a committee structure and you can instead of having a committee be a subset of validators, you have a committee basically be a cluster of computers that are logically presenting as a validator.
Exactly.
When you run into any type of sequential, non-sequential workload, you run into data fetching problems, like just inherently, right? Whether it's within like, oh, core 14 needs data that's waiting on core 2, like
100%.
things get messy inside of a CPU now that it's not a one chip anymore. It's, depending on how you count, somewhere between 60 and probably 200 chips, or cores all in, or logical units all within one die. Now we're externalizing that into, as you said, maybe 20 mid-grade servers or 5, very powerful servers. Like, every time you, like, even today on like an Intel CPU with like 24 cores, like the folks who are working on FireDancer have to think very carefully about what process is on which core because it affects how data moves through the system. I would assume that problem gets larger when you're dealing with, even if you've got 100 gigabit, InfiniBand fiber connected between all of these 10 machines, like your cluster still runs into certain amounts of those types of problems. So like, I'm curious, like, how fast can you get that communication? Like, what's the like Monad has a stochastic overhead because it's doing a lot of look ahead processing and certain amounts of that fail. You've mentioned there's a little bit of that in block STM as well.
Yeah.
Like, what does that kind of look like when you're talking about like a Shardines cluster, for lack of a better term? And like one machine needs data that somehow, because of some type of transaction, ended up on a different machine.
Yeah, so I think it comes down to the network latency, and then like the trade-offs are just different, right? So in a validator today, a single machine validator, you have the latencies you kind of mentioned, like there's a the latency of like context switching between cores.
There's
the latency
RAM
of
is very
RAM.
slow.
There's the latency to SSDs.
Yep.
And all that stuff. Now we're entering one more level of like latency of machines, right? And those can be sub-millisecond, but it's still going to be, it's still going to be non-trivial, right? And I think that's where you have to kind of build up, a lot. I mean, the best you can probably do is keep everything in RAM, make sure that the network is going to be, so it should be still faster than SSD, but it's going to be slower than, of course, accessing your local memory. And there are, I think you're very familiar with this. There's things like RDMA that can actually push a lot of this down to the network cards and kind of reducing latency and getting it pretty good. So it's probably a little bit slower than your main memory, but not a whole lot. And that means that, the problems that you bring up are kind of, in my mind, also last mile kind of optimization problems. Like the ability for us to process this shared state and then process each lane of the highway is still like really important, as long as we're not doing too much context switching between these and too much wasted work. It still provides a meaningful outcome. I think that's what we saw from the data ourselves, and the study we published there. So pretty excited about the technique, and I think, again, the goal for us is to demonstrate to people that this is a real possibility for seeing massive computations being done on a single validator that aren't possible today. Because it's not just a million TPS you can do. It's like, or I can do like at 1,000 TPS, I can do 1,000x more expensive computations, which is really neat, right? And so that starts to draw you into like, wow, my imagination starts to blow up a little bit more in terms of like very, very simple operations. I can do much more complex ones as well.
Yeah, I kind of wanted to get into a little bit of like, so Mega ETH was the first network I saw that was looking at node specialization, which was back in 2022, which I think was one of the really fascinating things about that project was like, the sequencer is only going to do inclusion. Okay, fascinating. The RPC network is going to effectively crank execution. Super interesting. We're going to throw a bunch of ZK provers in there for like state transmission. Sure, why not? Like this, you get something that feels like very kind of experimental and new and interesting. When you're dealing with basically different flavors of Shardines clusters, I assume that you have a lot of different compute characteristics depending on if it's 4 really beefy servers or if it's 10 less beefy servers. Like, do you start to think you get into situations where like certain types of transactions are too heavy to be processed by certain parts of the network? Like, how are you thinking about like the practical implementations of that amount of variance in what a logical unit of a validator actually is at this point?
It's a great question. I think today we really rely on the BFT model of computation, which means that 2/3 of the stake is going to agree on the computational outcomes. And to your point, though, that can be expensive for certain types of applications. And for payments, I think it's fairly expensive on Aptos.
Yes.
But there are much more, like say you want to do on-chain inference or something. That's something that would be very expensive to kind of replicate the computation across so many nodes. And I think this is where we're going to explore, like Aptos is exploring really different ways of, how do we provide decentralization that has different characteristics? Maybe it's 3 repeated computations or 4 repeated computations under a certain amount of stake, and allowing the users to kind of determine like their level of decentralization and cost trade-offs. And then also there's really interesting properties around how you can think about the trade-offs here when you think about like things like erasure coding, which allow different properties as well from the storage side. So it's an area of massive exploration for us, and I think things I'm sure you're excited about given your current position at 00.
Yeah, absolutely. I think that was one of the unexpected learnings of the last probably 3 years for me is like the compute side, I wouldn't say it's solved, but it's like we get straight arrow math at this point. Like we kind of know across every network like how you can handle the compute side of things. It's the data flow models that are like the Wild West at this point.
It's all data. I mean, I worked in supercomputing, and the sexy thing, of course, is to work on the compute and seeing how many teraflops are going to get done. But the reality is, you're bottlenecked typically by the I/O side, and that was the side I focused on. Not so sexy, but parallel file systems, parallel I/O algorithms are definitely the area that are really the most critical for getting scalability.
Yeah, I think Kevin Bowers has some stories about getting kicked out of supercomputer planning meetings for only focusing on throughput and I/O and not listening to anyone who says, no, we have to focus on the compute. The compute's useless if you can't load the program.
That's right.
So.
I mean, yeah, exactly.
So I do want to talk about Move a little bit too, and not as much like Move the language because there's podcast ad nauseum on Move but we basically have 3 different versions of Move at this point is what I hear from devs is like the movement move, the SUI move, and the Aptos move are all like it's not EVM. It's not like, okay, we're just going to copy pasta like pancake swap onto every other network. Like there are real programming differences at this point. Like at what point do you guys think you should rename them?
Good question. I mean, I think Move's philosophy is the one that I think is the most important here in this case. I mean, the philosophy of Move was rather than think about traditional programming where you write some code, you test it out, it doesn't work, you have a bug, you fix it, you kind of roll forward and move on. Like, what if you had a way to have less bugs introduced into your system because you're concerned about the fact that every bug here might be the difference between, losing all the money in the protocol, your livelihood, people's life savings, versus just like, I'm going to fix it going forward. And so the idea is really like thinking about programming languages from a different perspective. And so I think that part has been pretty much well maintained across all the different variations of Move. But there's really, I think I would kind of have a different view that there's really just 2 kind of flavors of Move. There's what Aptos has done and what SUI has done. And SUI has been kind of having to adjust Move based on their fast path. And we've not taken we take the stance that fast path is actually not great because of the fact that it doesn't affect things that really help people with this shared state. And introduces overheads to the system and has a different kind of, they had to make a lot of modifications to Move just to support that. And so we've really been trying to focus on how do we push Move into being much more functional in terms of things like dynamic dispatch that's very safe because it's something that kind of core Move doesn't have, or making sure the Move prover works. And that Move prover is allowing you to now have formal verification over specifications you determine into your code. It's like the best unit test ever because it tests every single input-output combination and makes sure that this characteristic is going to be upheld, which is incredible. And we've been delighted to see that the variant of Aptos Move has been used in so many different platforms from Roosh to Supra to Pontum to Movement and Inisha and others. And so, I think that having that community as well has been amazing. There's a small but very dedicated community of developers that keep looking across the language, seeing what developers are looking at, and then kind of pushing that forward in all the different places. is neat and fun to
Yeah,
see.
definitely. I think it's been interesting to look at like you see this sort of bifurcation, I think, in the blockchain space right now, where you have folks gravitating towards things like Move for all the reasons that you specified, and then you have people being like, we got to get back to C. And it's a really interesting kind of like juxtaposition. Like, what do you think is going on there from a developer side of things? Because you guys obviously like you're not building Aptos in Move, right?
Right,
Like
right.
there are different languages that you're using for different pieces. There's sort of been, I don't know, like Apple kind of was like started doing this, right? Where they were like, you originally used to be able to write iPhone apps in C or Swift, and now we're pushing everyone into Swift. And like that is just the only thing you're kind of allowed to write in at this point. Um, and there's sort of a few different theories I've come across as to like what's going on there. The first is like on a developer at an iPhone side, like the CPUs get so fast, like who cares if there's like programming language overhead for these things. And the other version is just like the average quality of developer has gone down. And so yes, you're saving people time. And yes, you are in some ways boxing out some folks who might want to actually be like, no, like I want to write this thing in C because it's like a DeFi swap and all these types of reasons. What is kind of like the Aptos answer to that for because we had this problem on Solana where like a lot of people built with Anchor and they hit a point where they were just like, oh, I want to do real Rust things or I want to do real C things. And obviously Move is like a real language and you can do a ton with it, but like there are limits to any programming model that prevents you from writing over your system memory.
Yeah, I think this is a really good call out. How can I say this? I mean, I've written on many different languages. I think, well, I have a couple thoughts. One is I think the programming language thing is kind of overblown to some degree. Like
Agreed.
every programmer has written like in 5 languages in their life. And so like
Yes.
learning one more is not the end of the world really. And I think Solana would probably agree with that thesis. The next thing though is going to be, I think this is where things like Java came around, and I think grabbed a lot of people's attention because of 2 things. One is it's very easy to code in Java. The barrier for entry is much lower than C, and the library support is just amazing. Like Maven is a huge repository of libraries that are just incredible. Like if you've thought of it, it's already been built for sure. So those 2 things have been advantageous. I'd say for Move, the view we have is, the great thing about it is it's a language that is not that it can grow and it's not like established like EVM now, where it's very, very hard to make changes, right? And so
right.
And then going back to my earlier point, the space is so early, it's hard to think about all the things you're going to need up front in a language without being able to evolve it. And so we've been evolving Move a ton. We're already, to your, you actually had a pun earlier with like Move 2. Move 2 has been a new thing for us where we've been kind of pushing like a lot of new syntactical sugar, a lot of new improvements in terms of higher order functions. And also the way the syntax is just so much simpler to use going forward. And that's something that's only possible because we can keep pushing the language faster and faster than anybody else can do it in the space. We're not tied to anybody. We can keep driving that forward, and the developers love to see like, wow, my code is 70% smaller than it was before because of Move 2, for example. But for your point about like making certain operations very, very, very powerful and also very performant, this gets back to me thinking about like Java and intrinsics. So in intrinsics in Java allows you to kind of access native functions through the language, and so you can think about certain primitives in Move that can be kind of Rust implemented and very, very performant and fast. If you want to write assembly or write C code, you could do that. But this kind of is limited to like a set of like trusted operations, whether it's cryptography or other things that make sense to do so. And that's where I think it's a really nice balance of like having that super safe kind of Move coding environment with formal verification and all the bells and whistles, and then also having the ability for super performant operations by adding them at the kind of Move native function level. And supporting those, looking at those very carefully because they're very dangerous, obviously, but having that ability to do both. So it's, in my mind, the best of both worlds.
So I guess kind of before we wrap up here, like I'm curious going forwards, do you guys have a lot of like stuff you've put out from performance characteristics of sort of like new roadmap for like Aptos into 2025? The piece that I think I underestimated because I've spent the last 4 years in the Solana ecosystem and now at 00 is like there are not many networks out there right now that are like transaction saturated, right? And I think you brought this up in kind of the beginning about like you guys were like, we're gonna build the infrastructure first, then we're gonna go out and get all the applications and that sort of thing. What are those like recruitment conversations like when you're trying to tell someone like, hey, look, you should expand your EVM protocol, your Solana protocol, you should learn Move and build something here, or for the net new developers coming into the space, it's like, hey, you should build something here. This was like one hell of a tough task at Solana. And so like I'm just curious how people are thinking about it in 2025.
I think it's about going back, and you asked this question earlier, I didn't answer fully, but I think the thing is, what can you do here you can't do anywhere else? And so a good example would be what Pact announced recently with microfinancing. They've issued, I think, more than $1 billion worth of loans, and they're on Aptos, and they might be very small loans, but you can do like a loan for like $1. You can repay in 2-cent increments, and then all the repayments combined are like under a cent.
Yeah.
And that's something that's really neat, right? And so it's a really nice area for us to see that kind of emerging markets use case where they're saving 2/3 of the loan amount they would normally pay on a platform that's just open source, open permission, and like available worldwide. And that's the kind of things I think are really interesting. The other thing that's interesting is now we're seeing some of those large internet partners really taking a look at Web3 and saying, look, for the first time, we feel like this infrastructure can actually handle our workload. They can handle tens or even hundreds of millions of customers transacting on the blockchain. We've seen your evidence of being upgraded with no downtime. We've seen that you can support massive throughput. And now we're ready to take a bet and build something really, really massive that we know is going to have tremendous scale at thousands of transactions per second on something like Aptos. And so that's also very exciting to see. But, I think there's also great things in the trading space that we talked about, like, having like block times today. Aptos is the fastest block times. It's sub 200 milliseconds. We're going to see those drop to 50 or even 100 this year, which is going to enable massive opportunities for kind of real-time money movements and real-time trading activities that aren't possible in the past. And so I think kind of continuing to push that envelope in technology will unlock the imagination of a lot of the application builders out there. And there'll be far better ideas than the ones I described, I think, coming on chain, since there's so much more creativity in an ecosystem than just one person.
Awesome. Well, Avery, thanks for joining us today on Validated.
Thanks for having me, Austin.